We're going to move to a new chapter today on sequences and series. A sequence is basically just an ordered list of terms. So you'll see I have a couple listed below. First one, 1, 5, 9, 13, 17, has 5 terms in it. And you'll see there's kind of an order of an adding of 4. In this next sequence, I have a and 3a plus 1 and 5a plus 3 with the dot 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 at the end. That dot 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 means it goes on forever, so there's an infinite number of terms. Any sequence that ends is finite. Sequence that never ends is called infinite. Now, as far as notation goes, here's another sequence, 2, 5, 8, 11, 14, all the way to this a with the subscript n. The 2 represents the first term, the 5 the second, 8 the third, etc., until I get to this last term, which we call the nth term. Notation for each term: the first term is represented by a with the subscript 1, second term a with the subscript 2, all the way down to the nth term, which is a subscript n. And different books from different publishers will use different notation for this. Ours uses the a with the subscript. Other books I've seen use t. Some books use s. If I want to generate terms in a sequence, I need a formula to do that with. And I think the easiest formula to work with is something called an explicit formula, because what an explicit formula does is it allows you to pick the term that you want in the sequence, plug its associated number in, and get that item out. For instance, if I want to find the first 3 terms and the 10th term in the sequence described by these explicit formulas down here, all I really need to do to find the first term is say, I want n to represent 1. So a sub 1 represents my first term, and then therefore every n is going to have a value of 1. So this is 2 to the first minus 1, which is going to equal 1. If I want the second term, I let my n value equal 2. Then I have 2 squared minus 1 is 3. Third term, 2 to the third minus 1 is 7. And 10th term, let n equal 10, so I have 2 to the 10th minus 1 is equal to 1023. You'll notice I have multiple values of n in this next problem. Works the same way. First term, n equals 1, therefore everywhere I see n, I plug a 1 in, and I end up with 3 halves. If I want the second term, plug a 2 in. It's 4 times 2 minus 1 over 2 times 2, or 7/4. Third term, 4 times 3 minus 1 over 2 times 3, which is 11/6. 10th term, 4 times 10 minus 1 over 2 times 10 is 39/20. Writing an explicit formula is a little more challenging than just plugging numbers in. You have to think a little bit, and for now we're not going to have a way to necessarily cookbook it. In other words, easily generate a formula. We're going to have to think through this a little bit. So the idea behind generating an explicit formula is letting n equaling 1 in your formula, and every time you plug that 1 in, you get this term out. When n equals 2, you'll get this second term out. When n equals 3, you'll get this third term out. When n equals 4, you'll get this fourth term out. Now, as seen in our previous examples, these equations can either be 1 line, 2 lines, have fractions in them, what have you, whatever it takes to get the answer we want. And you'll notice in this case, this problem's not too bad, because if n equals 1, I get a 1, n equals 2, I get a 2, etc., and you'll notice all the numbers below are just 1 more than the number above. So if I let my explicit formula be the nth term is equivalent to n over n plus 1, that gets every single term in my list. In the second term, or the second sequence, we do the same thing. N has to equal 1, 2, 3, etc., etc. And go through a whole series of guesses, if you will. It doesn't look like there's any additive pattern here. If I multiply by 2, then that's not going to work. Let's take a look at powers. If I square 1 and square 2 and square 3 and square 4, notice every time I do that I'm one off of my number. So if I take and make my nth term equaling to the subscript squared plus 1, that'll get me every number in that set. This last one's the trickiest. You'll see that this also has some kind of power function within it because I have 1, 8, 27, 64. These are all perfect cubes. Alright? So if I were to take and go n cubed, that would almost get me there. However, first term's positive, second term's negative, third term's positive. By plugging in 1, 2, and 3, I'm not going to get that alternating power. If I were to take and say, well, what if I had a negative n cubed? Then in my first term, I get a negative 1. So that's not going to work. I need to have some way to change the multiplication of 1 and negative 1 to this. And I just kind of gave you the hint. I'm multiplying negative 1 in an alternate sequence. So rather than making this to the n power, in which my first term would be a negative, I raise negative 1 to the n plus 1 power. In so doing, I get an even power for my first term of negative 1, which makes this positive. On my second term, I get my 8 here, and 2 plus 1 is 3, negative 1 to the third power is negative, and it alternates through. This is kind of like a negative counter, if you will. And that's my own little word for that. So that's how you write some explicit formulas. Again, it's a little guess and check work, but I think you can get through it at this point. Recursive formulas are much different than explicit formulas in that they use previous terms to generate the next term in the sequence. So you'll notice here's a sequence of 2, 5, 8. There's a pattern of adding 3 to my previous term to get the next term. And in essence, that's really all we need to do. We need to add 3 to previous term. Now the way I say that in terms of a recursive formula is I say my nth term is equal to 3 plus my previous term. And the way to say your previous term using sequence notation is a with the subscript n minus 1. That right there means the previous term. So now if I want to generate my first 4 terms of the sequence, the caveat is that you're given that first term so you can generate the ones after it. So if I want my first term, which I know is 300, and I'm trying to get my second term, then this says 1/5 times my previous term. My previous term, I'll just write this out one time, is a sub n is equal to 2 minus 1 plus 10, which says the second term is equal to 1/5 times my first term, which is my previous term, plus 10, or 1/5 multiplied by 300 plus 10, which is 70. Now I'll expedite this a little bit. So this time, to get my third term, I'll make this a little bit quicker and say I've got 1/5 times my previous term, which is the second term, plus 10. And I have 1/5 of 70 plus 10, which I believe is 24. To get my fourth term, I take 1/5 my previous term, which is my third term, and add 10 to it. That gives me 1/5 times 24 plus 10, or 24 over 5 plus 50 over 5, 74 over 5, and that's my fourth term. Let's do this for a couple more sequences just to get the hang of it. I know my first term is 10. I want my second term, which is found by taking 1 over my first term. That's the previous term, which is 1/10. Get my third term, I take 1 over my previous term, which is my second term. So that's 1 over 1/10, which is equal to 10. And then my fourth term is 1 over my previous term, which is my third term, or 1/10. You'll notice in this next example, I have a previous term and a value of n in the denominator. So notice how this will work. I want to find my second term, which is my first term, over my subscript, because that's the n value of 2. So in this case, my first term was 12 over 2, which is 6. To get my third term, I'm going to take my previous term, which is my second term, over, now in this case the n value goes to 3 because that's my subscript. So I've got 6 over 3, which is 2. To get my fourth term, I use my previous term, which is my third term, over, notice my n value is now 4. And my third term was 2 over 4 is equal to 1/2.